All right, I want to do a little thought experiment that explains why you can think of surface tension as being a force per length of interface exposed. So here's the way I'm going to do this. So imagine that I have a wire, let's call it a U-shaped wire, where I put in this little sliding wire that's shown here on the picture on the right-hand side. And then in between where that wire makes sort of a square shape that I've drawn here, I'm going to put a liquid, I'm going to fill it basically with a liquid that forms a taut interface. So it's a thin sheet of liquid, so it's actually got a front and a back face. So it's actually got two exposures from air to liquid, one on the back side and one on the front side. And then what I'm going to do is I'm going to take the sliding bit of wire and I'm going to slide it forward in amount delta x. When I do that, I'm going to increase, so the liquid film will basically expand along with the sliding wire, and you'll end up with a larger surface area. So how much energy does that add when I slide that wire forward? Well, that's just a change in energy equal to the surface tension times the new amount of exposed area. So the extra amount of area that I'm exposing is surface tension times 2 times delta x times the width w shown up here. So 2 because there's both a front and a back air liquid interface. So there's 2 of those interfaces being exposed when I slide forward. Now that energy has to be provided by the applied force that we're using to slide the wire. If we look at the form of the change in energy, it's proportional to a change in distance. And the proportionality constant must be the applied force. So the applied force is apparently the surface tension times 2W, which happens to be the length of the perimeter of the exposed liquid-air interface. So if we think about doing that process of pulling it apart very slowly, we can make a free body diagram for ourselves where we balance the force that we're using to pull by a force that must exist at the air-liquid interface that counters it. Otherwise, we wouldn't be in equilibrium. So there must be some sort of force pulling back on the film. So what I'll do is I'll highlight 2 line forces that we'll postulate to exist that basically act along the air-liquid interface in the opposite direction of the force that we're applying. Each one, just by deduction, must be equal to the surface tension times W, which happens to be the length of that line, right? So W is the length of each line. There are 2 such lines, so the force turns out to be 2W times the surface tension, where 2W represents the exposed perimeter of the air-liquid interface. So in summary, even though surface tension is really fundamentally comes from the fact that there's an energy penalty for forming a surface area, it turns out that it's equally valid to think about it as a force per unit length that acts across any exposed air-liquid interface. And it'll turn out that that's actually a beneficial way of thinking about it for setting up engineering problems that have to do with surface tension. And I'm going to show you some examples of that now.